Mission Atlantic, to ensure a sustainable future for the Atlantic Ocean. Integrated Ecosystem Assessment, or IEA, is a holistic approach to managing ecosystems by evaluating the cumulative impacts of natural variation and human activities. It follows an IEA loop that starts with scoping the system, together with stakeholders developing indicators, analysing the risks from and to different parts of the system, testing potential future scenarios under natural and anthropogenic change, and refine focuses on revising and improving the assessments based on the outcomes and insights gained from earlier stages in the cycle. This process helps balance trade-offs between ecological health, social well-being, and economic viability, ensuring sustainable use and conservation of ecosystem services. The risk analyses phase identifies and evaluates potential threats, quantifying their likelihood and impact. Risk analyses pinpoint parts of the system that require attention today, but also in various uncertain futures, ensuring long-term sustainability and resilience. In this video, we explore quantitative risk assessments in support of ecosystem-based management. Our guide, Susa, explains how the qualitative risk assessments from earlier in the IEA process informs this more quantitative approach. We see how the Bayesian belief networks employed in Mission Atlantic start and end with intuitive networks and probabilistic results, and how established models can be updated and expanded as new data become available and systems change. Using a simplified example, Susa demonstrates how BBNs are structured, trained, and utilised.
Hello, and welcome to the Mission Atlantic e-training on integrating multiple evidence in quantitative risk assessment. My name is Susa Niiranen, and I'm a researcher at the Stockholm Resilience Centre in Sweden. I also lead the risk assessment work in Mission Atlantic. So why should we care about the risk assessment in the oceans, and particularly why now? We all know that the climate change has moved on at unprecedented rates, affecting our oceans during the past decades. But also many of the ocean sectors, they have grown exponentially since late 90s and early 2000. And this means that we humans also, we are expanding towards the ocean. At the same time, we have started to learn that these ocean sectors, they do interact with each other as well as the ecosystem. And this could create even quite unexpected effects and risks in our oceans. And also as scientists or researchers, we are part of this network. So if we define risk assessment, the most general definition is that it quantifies the probability of undesirable events and their consequences. If we go a bit more ecological, we could say that risk assessment, it qualitatively or quantitatively determines risk to an important ecosystem component given change in ecosystem pressure or management actions. Risk assessment, it's also an integral part of the Integrated Ecosystem Assessment, the IEA. And you can see in this loop here that risk assessment, it really comes in the middle after the scoping for the key issues, designing and defining indicators, and then the risk assessment is the next one. And risk assessment, as well as the entire IEA, it is optimally tailored for certain well-specified management need or question. So in Mission Atlantic, we use something called hierarchical risk assessment approach. And this means that we go from simple to more complex. It means that we go from single pressure, single object or component towards multiple pressures and multiple components. And this means that if we go towards more complex, we can also account for indirect interactions in the system. We also go from qualitative to quantitative. And this we do by scoping. So if you take a look at the triangle here, at the bottom of that we have, at the beginning, we have all the risks laid out on the table. After that, there is a stakeholder engagement and expert engagement. And with stakeholders and experts, we do a qualitative or semi-quantitative scoping of these risks. And this scoping narrows them down into certain key risks that we then look into using quantitative risk assessment tools and also multiple sources of evidence. So the Mission Atlantic Risk Assessment map, it is pretty simple, but it may be useful to some of you planning your own risk assessment work. So we start off with the scoping for key risks in our systems, and our systems are ocean systems. So the key sectors we could find out, they are things like fishing, shipping, it could be, for example, renewable energy. Pressures, there's pressures like noise, species extraction, contaminants. Ecosystem components, we have things like mangroves, we have certain fish species, and we have, for example, rocky shore habitats that we look into. Mission Atlantic also, we have 7 case studies. You may have only one, but for each case study, we do the scoping separately. And the methods we use, we run stakeholder workshops, and the method used here is ODEM. And if you want to learn more about this ODEM, please take a look at the previous e-training models of Mission Atlantic. And this scoping, it really is the beginning of also the IEA Integrated Ecosystem Assessment cycle. So the second part then, or step, it is the quantitative risk assessment that then is tailored to case studies and stakeholder needs via the scoping process. So now we know the key risks we should look into, and we do that by using Bayesian belief networks. And this is a good tool because it can combine evidence from multiple sources, such as monitoring time series, model results, expert knowledge, etc., and actually produce quantitative risk assessment results. So Bayesian belief networks, we often call them also BBNs. They are probabilistic directed network models. And in these, each variable, which is called also node, it possesses a probability distribution. And between these nodes, there are conditional probability distributions set. And this means because we are talking about network models, we can study interactions such as we showed at the beginning of this presentation. Also, the results of these kind of models, they are quite easy to communicate, particularly within the risk context, because we get probabilities out. And just an example, I could say, and this could be out of a Bayesian belief network, probably not an ocean one, but I could say that there is a 70% chance for rain this afternoon if the weather is cloudy and temperature is high in the morning. And I don't know what you would do in this situation, but just wait a second. I would take an umbrella with me if I went anywhere that day. And as I said earlier, these models, they can combine knowledge from multiple sources, qualitative and quantitative, and this is really a strength of this approach, particularly if you work with a case where only little data is available. Because you can't define what the stakeholders actually scope as the key risks. So you don't really necessarily have all the data available for your study either at the beginning. And these models, they can be updated or expanded. They are modular. So this really makes them fit for the IEA. So if you have watched the earlier teaching models of Mission Atlantic, you know by now that the IEA is actually a continuous process. It's a loop that keeps going and going. And once we go around this loop, the results and the methods and maybe even the questions, they should be refined at every time you go around it. So then I have created a simple toy model to explain a bit more in practice how do the Bayesian belief networks look like and how the output of them looks like. And I'm going to present to you this process in 3 different steps, creating a model. It's a very crude estimate of the actual things that you need to do, but it gives you a bit of an idea how to proceed with such kind of models. You should also remind yourself that even before the step 1, you've done the scoping process. So you start with a clear research question that you are going to tackle with this kind of risk assessment. So in the step 1, we define the model structure, and I have defined a very simple model here. I have temperature and I have the fishing effort at the top. They are affecting the fish biomass, and the fish biomass and the fishing effort are affecting the catch at the bottom. The nodes that are affecting another node, they're called parent nodes, and the affected nodes, they're called child nodes. And this kind of model structure, it can be defined either by using numerical data, for example, time series, and some of the programs, there are certain programs that can build these kind of Bayesian belief network models, commercial ones such as Huggin or Netica, but you can also do this with R. But some of these can actually derive the structure automatically from the data. Or you can use expert knowledge, or the combination of the two. The key part here is the second step also, that once you have the suggested structure, you should optimally evaluate it with experts or stakeholders before you proceed to parameterizing the model. So step 2 then is the model parameterization, so putting numbers to things. And for management purposes, it often makes sense to discretize the data you have. So it means you bin the data. Here in every node, I have binned it into 3 different bins. For example, in the case of temperature, I've binned it to decreasing temperature, current temperature, or increasing temperature. Then you assign the probability distributions between the parent and child nodes. And you can use here expert knowledge of qualitative data, and once again, and/or time series or experimental data. Then comes the step 3, which is actually very critical, particularly if you use these models for management purposes. This is the model evaluation. And it's all models that should really be evaluated for their performance. And if you have sufficient numerical data, some of it should be left outside the calibration process for model validation. If you don't, which is often the case, you should have independent experts to evaluate the model performance. And now you will be my independent expert. I've created this relatively simple model, and you can judge in the end if it makes sense and if it's usable anywhere. So I will explain a bit. I have run one scenario with this, where I have increased temperature and decreased fishing pressure. This means that I have 70% chance that my fish biomass actually increases or is high, but I also have 5% risk that is low or decreases. With a catch, it's a bit different story. So I have 7% chance that I actually get higher catches, but 47% chance that I get lower catches than today, due to the decreased fishing effort mainly. So it's up to you to judge if it makes sense. So finally, how applicable are these risk assessment results? And I think when you appropriately apply the methodology and use the data, for example, you make a model that's context specific and focuses on stakeholder priorities, you use relevant data and knowledge, and you really validate your results and model. In that case, I think the BBNs particularly, they can really inform the IEA process and ecosystem managers on risk and trade-offs related to interactions between different system components. And I showed you a very simple example, but you could do this to study, for example, interactions between different sectors like shipping, fishing, and agriculture, land, if you wish. And then these models, they clearly actually communicate the risks and related uncertainties because all the results come out as probabilities. So it's really suitable to inform both risk and the uncertainty. And with that, I would like to thank you for your attention. And please take a look at the other e-training models of Mission Atlantic as well.